So imagine that we have this graph. This function over here is absolute value of x times x minus 3 over 9 minus x squared. So say that we wanted to find the limit as x approaches 3, which can be written like this. The limit as x approaches 3, and let's call this f of x, So the first thing that we're going to try here is we plug it in. So we get the absolute value of 3 times x is 3, so 3 minus 3 over 9 minus 3 squared. And if we simplify this, we get 0 times 3 is 0 over 0, 0 over 0. That is undefined, which we don't want. So if we look at the graph, as the function approaches x equals 3, it seems like it's approaching a very specific number, but when we're plugging it in, we can't find that specific number. So if we look at here, 3 is undefined, but everywhere else on this function, for the most part that we can see, seems to be defined. So how can we find what y value this x equals 3 has at this point, just by when we're given the function? So one way we can do this in this case, if we notice that our x minus 3, our 9 minus x squared at the in the denominator can be factored. So then we're left with the absolute value of x times x minus 3 over 9 minus x squared factors to be 3 plus x times 3 minus x. And now look at this. This 3 minus x and the x minus 3, they're the same thing, except they're opposite. So one is the negative of the other. So we know that if we were trying to simplify this, then we could cross these out and put a negative at the top. So now we're left with a function which is not the same function. It's the same in every respect, except that at this x equals 3, it's going to be defined. So now we have the absolute value of x over 3 plus x. So now let's see what happens when we plug in 3 here. So we get negative times the absolute value of 3, which is negative 3, over 3 plus 3, which is 6, negative 3 over 6. And then we get negative 1/2. And now if we look at this graph, as we take the graph closer and closer to 3, we seem to be approaching a very specific number. When we're at 2.98, we're at negative 0.498. And when we're on the other side, we're at negative 0.502. So those are both very close to negative 0.5, which is equal to negative 1/2, which means that this is a valid way that we can find the limit as x approaches 3 on this graph. So this also leads us to consider one-sided limits. So now instead of this function, imagine we had this. So this does not seem to be approaching a very specific value, but we would not know that from this, just given this function. Or even if we were given the graph of this function, we could see that the limit as it approaches it from the left, meaning if we looked from the left and got closer and closer here, if we got closer and closer to the value 2, if we're looking for the limit as x approaches 2, then it's approaching from the left, it looks like negative 1. So now if we do it from the right and look from this side, it's approaching also 1. It's 1 everywhere, and then here it just jumps. It's undefined at 2. But we can tell that from the left, it seems to be approaching negative 1, and from the right, it seems to be approaching 1. So the way that we write this is the limit, or I'll write it over here, the limit as x approaches 2, let's also call this f of x, and we'll do 2 from the left. We write from the left by putting a little minus sign up here. That means that we look from the left of the graph. We don't care what's happening over here. We only care what's happening from this side. So if we look, we're getting closer and closer, and it seems to be at -1 this whole time, and nothing changes up until this point. So the limit as x approaches 2 from the left is going to be -1. If we take that same logic and apply it to the right, from the right, we use the plus sign because it's coming from the positive direction of f of x. Then we look from the right, it's at 1 this whole time, then it just jumps to -1. So it looks like from the right, if we draw a line here and only look on the right side of this line, then we would only know that it's approaching 1. So that means that from the left, it's approaching -1, and from the right, it's approaching 1. So what can we do with this? This tells us that the limit as x approaches 2 of this function does not exist, because the limit from the left is different from the limit at the right. So we can write this formally by saying the limit as x approaches, or if the limit as x approaches, instead of, this isn't specific to 2. If this were any other number, it would work too. So instead of writing 2 to generalize it, we can write c. That's just some number that x can approach. So if the limit as x approaches c of some function, c from the left, is not equal to the limit as x approaches c from the right of f of x, then the limit as x approaches c of f of x does not exist. DNE stands for does not exist. Okay, and this is what we call a discontinuity. So this is an example of a discontinuous function because it jumps between these 2 points. And if we think about what we think of a continuous function to be, it doesn't have any jumps. It's just smooth and looks something like this. And doesn't have any holes or discontinuities or anything. So we can write that formally as the definition of continuity is what I wrote earlier, the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. So that we got because this is an example of a discontinuous function, and this rule did not apply there because this was a discontinuous function. So this is one condition, but sometimes also, if we had a piecewise function and a graph that looked something like, let's say this, and there's a hole here and a point up here, then the limit does exist. The limit from the left, we'll see here, is the same as the limit from the right. So the limit does exist, but the function is defined up here. So if we plugged this value into the function, we would get a value, but it's not the same as the limit because it still has a discontinuity. So if we want this to be included in our definition of continuity, we'll have to say and, or which equals f of c, which just means the y value at that point up here. So this is not continuous, but instead, if this point were filled in down here, then this would be continuous because this is f of c right here. The limit from the left is equal to the limit from the right, and that's the same as the value of the function here. So that's a general definition of what continuity is. So there are a few different types of discontinuities. This one is called a jump discontinuity. And this is what we call an irremovable discontinuity, meaning if we have the function here, there's the limit from the left and the limit from the right are going to be different. So this will always be discontinuous no matter what we do to it without changing the value. But if we had if we had a function that just had a hole in it. So let's say we had x squared plus 6 or plus 5x plus 6 over x plus 3. If we look at this function, everything seems to be okay. But if we look at the limit as x approaches -3, if we look for -3 here, as we get closer, -3 undefined. So how can we deal with this? It seems to be continuous. So this is what we call a removable discontinuity, or a hole. So the way that we can remove this discontinuity, if we have the function, then if we notice the top can factor. So this becomes x plus 2 times x plus 3 over x plus 3. And what do you know? The x plus 3's cancel out, and we're left with x plus 2. And when we plug in negative 3 for that into just the function x plus 2, we get -1, which, if we look at our graph, it's what it seems to be, roughly. This is -1, and that's what it's approaching from both sides. So whenever you see a graph, your first instinct should be to plug it in. If we plugged in -3 up here, we would get 0 in the denominator, which we can't have. So a way to get around this is to factor and remove this discontinuity by canceling out that common x plus 3 on the top and the bottom. So now another example of a discontinuity is a vertical asymptote. So this is the same function we had earlier, but if we look at x equals -3, if we look at x equals -3, we see something a little different. Here it's -2, and if we zoom out a lot, x is approaching -3 from both sides. Here it's -3.051, but it just keeps going up. It doesn't seem to approach any specific number. And if we go from the right, we're getting closer to -3, but it just keeps going down. So this is an example of a vertical asymptote, which we studied in pre-calc. And now the way that you'd find out that this was a vertical asymptote based only on the function is we would do what we did before. We'd have absolute value of x times x minus 3 over 3 minus x times 3 plus x. We'd cross these out. We'd have a negative on the top, negative absolute value of x over 3 plus x. Now, if we look here, this is our function with that removed discontinuity that was at x equals 3. But now at x equals -3, if we plug in -3 here, we get negative absolute value of -3, which is -3. Well, absolute value of -3 is 3, and then we take the negative of that, which is -3, over 3 plus -3 is 0. So now we still have something over 0, which we can't have. But notice this time, it's not 0 over 0, it's something over 0, -3 over 0. So that means that when we go from both directions, it's going to approach either infinity or -infinity. And this is what we call a vertical asymptote. And the way that you would know this, if we have anything over 0, it could be -3, it could be 500. If we have something over 0, then it's going to be a vertical asymptote at that point. So that's our other type of discontinuity. So we have a hole, a jump, and a vertical asymptote. And a hole is the only one of those that's a removable discontinuity. The other ones, the limit does not exist.